All right, so far we've spent a lot of time in the world of electrostatics, right? The physics of charges just sitting still. But now we're going to see what happens when those charges start to move. And believe me, that's when things get really interesting. This motion gives rise to an entirely new force, magnetism. So let's dive into this dynamic world where moving charge is king.
And if you want to get a sense of the sheer power we're talking about, just look at this. That's an industrial electromagnet, and it's lifting tons, literally tons of steel. And the craziest part? This incredible force is generated simply by getting electric charges to flow through a wire. That right there is the raw power of moving charges in action.
For centuries, people associated magnetism with lodestones, these weird, naturally magnetic rocks. But the modern understanding is so much more profound. The real source of all magnetism isn't the stone itself, it's the tiny, microscopic electric currents swirling around inside of it. At its heart, magnetism is just electricity on the move.
And this all came together in a really explosive period of discovery in the 19th century. I mean, look at this timeline. It all started in 1819, kind of by accident, when Ørsted saw a compass needle twitch near a current-carrying wire. That one little observation just opened the floodgates. Immediately, you have Biot and Savart trying to quantify the force. Then Ampere comes along and makes the bold claim that all magnetism is just from electric currents. And then, to top it all off, Faraday shows it works the other way too. A changing magnetic field can create an electric current. Boom. The two forces were unified. An absolutely incredible decade for physics.
Okay, so with this deep connection between electricity and magnetism firmly established, physicists needed a way to actually describe and calculate this new field, which we call the B field. But here's the twist. Unlike the electric field, which acts on any charge, the B field is defined by the force it exerts specifically on a moving charge. So let's get into the math.
This is it. This is the fundamental equation for the magnetic force, and you've got to pay close attention to the notation here. It's a vector cross product. That little x is everything. It means the resulting force vector, F, is always perpendicular to the plane formed by both the velocity vector, v, and the magnetic field vector, b. This perpendicular relationship is the absolute key, the defining feature of the magnetic force.
Now, if we just want the magnitude, the strength of that force, we unpack the cross product and we get this expression. F equals Q times V times B times the sine of theta. And that theta is the angle between the velocity and the magnetic field. So you can see right away this sine term runs the whole show. Think about it. If the particle moves parallel to the field lines, theta is 0, sine of 0 is 0, and you get absolutely no force at all. The force is at its maximum when the particle cuts across the field lines perpendicular to them, where theta is 90 degrees and sine of 90 is 1. So the unit we use for this B field is the Tesla, or T for short. And just to give you some perspective, the Earth's magnetic field that guides your compass is really weak. It's about 50 microteslas. The magnets inside an MRI machine, on the other hand, can be several teslas. That's a mind-boggling difference in strength, 100,000 times stronger or more.
Okay, so we've got the magnitude sorted out with that sine theta term. But force is a vector, right? We absolutely have to know which way it's pointing. The cross product gives us a formal mathematical way to figure it out. But how do we do it quickly? How can we get an intuitive feel for it?
Well, the answer is a physicist's best friend when it comes to cross products, the right-hand rule. This is our essential tool. It's how we translate the abstract math of a vector product into a simple physical action that you can literally do with your own hand.
And this is basically what it looks like. Your hand becomes this kind of analog computer for solving vector problems. Your fingers, the way you curl them, your thumb, they all directly map onto the vectors in that force equation. It's a really clever trick. So, let's walk through the steps, nice and slow. First, take your right hand and point your fingers in the direction of the velocity, v. Second, you curl your fingers towards the direction of the magnetic field, b, making sure you take the shortest path, the smallest angle. And wherever your thumb is naturally pointing now, that's the direction of the magnetic force, F. But, and I can't stress this enough, this is the part that trips up so many people. If your charge, Q, is negative, like an electron, the force is in the exact opposite direction of your thumb. You have to remember to flip it at the end. Always, always check the sign of the charge. All right, theory is great, but let's make this real. We're going to take our force law and our brand new right-hand rule and apply them to a classic textbook problem. We'll use an alpha particle, which is just a helium nucleus, so it's got a positive charge. Okay, here's our setup. Imagine we have a big, uniform magnetic field. Let's say 1.5 Tesla, and it's pointing straight up, along the positive z-axis.
That's not going to change. The only thing we're going to change is the direction we fire our alpha particle into this field.
Let's work through this table together. Using the rule, case A, velocity is along the positive x-axis. So fingers along plus x, curl them toward the B field, which is plus z, and yep, my thumb points in the negative y direction. The angle's 90 degrees, so we get the max force. Now, case B, velocity is along negative y. Fingers point down the negative y-axis, curl toward plus z, my thumb now points along the negative x-axis. Again, max force. But now look at case C. This is the important one. The velocity is along the plus z-axis, exactly parallel to the B field. The angle is 0, and the sign of 0 is 0. The result? No force. None. A charge can fly right along a magnetic field line and feel absolutely nothing.
And this brings us to a really unique, kind of weird consequence of the magnetic force. We've just established that this force is always perpendicular to the velocity. This has a really profound effect on how the particle actually moves. So just think about that for a second. If you have an object, and it's moving, and you start pushing on it, but you always push at a perfect right angle to its direction of motion, what kind of path is that object going to take?
The answer is uniform circular motion. Because the force is always perpendicular to the direction of motion, to the displacement, it can't do any work on the particle. And if you're not doing work, you're not changing its kinetic energy, so its speed stays constant. A magnetic force can't speed a particle up or slow it down. All it can do is change its direction, acting like a perfect centripetal force that just swings the particle around in a circle.
Now, to visualize these fields that are causing all this circular motion, we draw magnetic field lines, and they have some very strict rules. The direction of the field at any point is just the tangent to the line. Where the lines are dense, the field is strong. They can never, ever cross. But the most important rule, the one that defines magnetism, is the last one. They always form continuous closed loops.
And you can see that principle so clearly here. Whether you're looking at a simple bar magnet or the entire planet Earth, the field lines always form these complete loops. They emerge from what we call the North Pole and loop all the way around to re-enter at the South Pole. This is totally different from electric fields, which start on positive charges and end on negative charges. Magnetic fields don't start or end, they just loop.
So let's end on a puzzle, a little bit of a paradox. We've just established that the fundamental magnetic force on a single moving charge does no work. It can't add or remove energy. So, how is it possible that we use this exact same phenomenon to lift a massive, high-speed maglev train off its tracks and propel it forward? Answering that question connects these deep fundamental principles to some incredible real-world engineering. And that's a great place to leave it for now.